Well, thank you for inviting me to speak today. I am Kelly Lively. I'm the Department Manager for Radioisotope Power Systems. I work primarily at the campus at the Materials and Fuels Complex, and it is my pleasure to talk to you about radioisotope power systems today. I would like to start out with stating that we work in cooperation with the Department of Energy, Office of Nuclear Energy, in continuous rate production supply chain. And this first slide just is an illustration of the other national laboratories in the DOE complex that we work with. So in order to provide the nuclear power systems that we provide to empower deep space missions, we do work with other national laboratories. The Department of Energy has reestablished PU-238 isotope production. Oak Ridge National Laboratory is the lead laboratory for that, and they are the ones that supply the neptunium targets that are inserted in Oak Ridge's HIFER reactor and IANS ATR reactor. Those neptunium targets are irradiated, and the PU-238 isotope that is generated from that irradiation is used in the supply chain to make the fuel at Los Alamos National Laboratory. The PU-238 is pressed into ceramic pellets of plutonium oxide fuel. And that's the picture that you see in the upper right-hand corner of this slide. It is then, after it is pressed into the ceramic pellet, it is then encapsulated in iridium. The iridium-clad vent sets that the PU-238 pellets are encapsulated in are also provided by Oak Ridge National Laboratory. And then those are sent back to Idaho. In the bottom left-hand corner, you see there two glowing cylinders. They're about 2 inches in diameter and about 2 inches tall. Those are the ceramic pellets that are encapsulated in the iridium. And they've gone through some processing here at Idaho National Laboratory, but they are the glowing red and really the heartbeat of what we do. INL is involved because we handle the radioactive fuel and we assemble the nuclear power systems, one of which you see there in the lower left-hand corner. And that's the one in particular that I'm going to be talking about today. It is a multi-mission radioisotope thermoelectric generator. It is why we probably have acronyms. We refer to it as the MMRTG. That particular one is Flight Unit 2, and it will be used to power a land rover going to Mars this July. And while we're at it, we'll talk about the launch support that we provide at Kennedy Space Center for launching whatever we're going to be powering, in this case for Mars 2020, a land rover named Perseverance just recently will be stacked inside that white fairing that you see at the top, and we will be shooting it off to Mars during the launch window, which has been established from July 17th of this year through August 5th. So I will be deploying a team of about 25 personnel from INL that will be supporting this mission down at the Cape. So a little bit more about the mission. Our RPS programmatic mission, as I stated before, is to fuel test and deliver radioisotope power systems and related technologies for use in remote, harsh environments such as space. These radioisotope thermoelectric generators are just that. They are electrical generators that convert the heat generated from the decay of the plutonium oxide fuel that you just saw in the last slide into electrical energy using thermoelectric devices. The pictures illustrate two of the different systems that we have fueled and tested at Idaho National Laboratory. The upper right-hand corner is the general purpose heat source RTG, and it generates about 300 watts of electrical energy. And the other is the MMRTG that powers the Mars Science Laboratory Curiosity and will power the Mars exploration rover Perseverance. A little bit about just how it works. The Seebeck effect is really the science behind it. This is an old technology. The program's only been at Idaho National Laboratory since around 2003, even though this is a 60-year-old program. It was moved here from Miamisburg, Ohio, back in in the early 2000s. This is just a schematic of the multi-mission radioisotope thermoelectric generator. I like to say that's why we have acronyms. We refer to it as the MMRTG. You see an illustration of it at the right. And you see the thermoelectric modules, which utilize the Seebeck effect in order to produce electricity. Not a real efficient system. We have about 4 pounds of plutonium oxide fuel in this power system, and it converts about 200 thermal watts of energy into about 120 watts of electrical power. So not real efficient, only 5–6% efficient, but it does supply the power needed for the mobility of the Land Rover that I'm going to talk about, in addition to powering all of the scientific instruments on board. A little bit of history about another mission. New Horizons was the first space mission that we supported here. You see in the upper left-hand corner here, the 300-watt electric series general purpose heat source RTGs, and this is a picture of New Horizons that you see over here in the upper left-hand corner. If you didn't recognize me, I am the cute second one from the right in the bunny suit. Serving in a different capacity for New Horizons than I do now in my management positions. And then this is the most recent picture of our team supporting Mars 2020. This is the transportation and integration team, and this was during the delivery and hot fit check of the MMRTG that's supporting the Mars 2020 Land Rover Perseverance. You see some vital statistics here in these windows. Okay, capabilities. We work in a lot of different places. At INL, we do primarily our largest amount of work in SSPSF, which is located right here in the Pitus area. We also have some laboratory spaces that we operate, one of which is the Engineering Development Laboratory, also at MFC. We also have some laboratory spaces out at InTech as well that we utilize. What exactly do we do? As I mentioned, the reason that we're involved is because we can handle the radioactive fuel. This is a shipment of the fuel from Los Alamos National Laboratory in our 9516 casks. You see an operator here opening up the stainless steel containment vessels to eventually get down to the iridium-clad general purpose heat source fueled clads. We take that to another area of our facility, and inside a glove box is where we actually insert 4 fuel clads into each general purpose heat source. That's what you see here, is the fueling process inside that glove box. You see a quality assurance inspector and an operator. They're looking at serial numbers. As you might know, there's a lot of rigor involved in the assembly of these units. Private industry provides us with these radioisotope power systems. Oh, my boss is calling me. Let me decline that. Private industry provides us with these power systems, and you see the receipt of the MMRTG in these pictures. This one was designed by Teledyne Energy Systems Incorporated out of Huntsville, Maryland, and it was built and tested with electric heaters in it by Aerojet Rocketdyne in Pasadena, California. Once we get our fuel and build them into general purpose heat sources, and we receive the flight MMRTG from the from private industry. We move all of those items into the inert atmosphere and assembly chamber, also located in SSPSF. You see operators in the center picture inserting the MMRTG inside this small hot cell. And then the atrium door is closed, and we bring this to an argon atmosphere. It takes us about 3 days to flood it with argon, and then we stack and insert those general purpose heat sources into the central cavity of the power system, and that's what you see in this picture. This is the fueled stack of 8 general purpose heat sources, and here it's being inserted into the central cavity. Again, just showing the fuel clads that are contained for each of them in each of these 8 modules. Once we get the system fueled, we take it out of the IAC, and it will stay outside in an air atmosphere until it's launched into the vacuum of space. And we perform a suite of acceptance tests on it. You see here some Lexan shielding, and this is the radiation shielding that we use to protect our operators and folks from the radiation of the MMRTG. As I said, we go through a suite of acceptance tests. All of these test chambers are located in SSPSF. The acceptance testing is designed to simulate the environments that the MMRTG will see during its mission. Vibration testing simulates the launch environment and re-entry into the Martian atmosphere. We have mass properties testing. You see the MMRTG on the mass properties testing equipment in the upper picture. We measure the center of gravity and the moment of inertia. The picture on the bottom there is just showing the weighing of this is non-flight hardware. We also literally weigh the MMRTG as well. This is a magnetics testing station. This is where we map the electromechanical characteristics of the MMRTG. You want to know the electromagnetic signal that it is generating so it can be filtered out from any onboard magnetic measuring equipment that the spacecraft may have, or the rover in this case. Lastly, we put it through thermal vacuum testing. This is a 6-foot diameter by 9-foot long chamber. We put the power system in here, pull a on it. We can also simulate the coldness of space, but this is where we will see the highest power output, and we monitor the power from this chamber for a couple of weeks just to ensure that it is actually generating power as it was designed to do. And then after that, as I said, we're a full service laboratory. We will transport the power system to Kennedy Space Center. And this is what you see here. And I'm going to give you a little more update on what's going on with it now. But this is our transportation trailer that you see over here. We have 2 of those trailers. Inside of those, as reflected in this picture, we can hold 2 9904 shipping casks. This is a double nested steel cask. The power system is inserted into it vertically, and this is how it's transported. These are unique casks. There are only 3 in existence. We are the custodians of those. We are also the custodians of these transportation trailers. All of those things, all of those components are stored out at Intech on the INL site. These pictures are actually taken at Kennedy Space Center, and I have some more pictures of them, but this cask is being disassembled, and inside of it would be an RTG. And this is inside the RTG facility down here at Kennedy Space Center. Over here to the right, you see the launch complex, SLC Space Launch Complex 41. I have some other pictures of it later on, but this is the vertical integration facility, the building that you see back here. That's where the rocket is stacked. This is a close-up picture of this building. And then there's a rail system that travels along this road and out to the center of the launch pad. You see 4 lightning arresters out here on the launch pad, and in this, and in the center of that would be where the rocket would travel to once it is stacked, the payload is in it, and we're getting ready for launch. Again, this is a close-up of the vertical integration facility where the rocket is stacked up, and this is, I'm going to keep doing that. And then this is a picture of the tool that is used to insert an RTG into the spacecraft. This is a mock-up picture of some training that we did with a high-fidelity mock-up qualification unit in Pasadena, California. Okay, so to Mars 2020 specifically, finally we get to it on slide 18. So we went through a naming process, or we didn't, NASA did. There were several names that were down selected. There was, NASA put on a competition with K through 12th graders and to come up with a name. And this seems to be the way NASA rolls for all of the missions. They did the same thing for Curiosity. But of all of the names that you see there, Perseverance was chosen. So hence, we now have a Mars 2020 rover, and its name is Perseverance. Perseverance, you can see over here, is in what is called the Payload Hazardous Servicing Facility. It's a clean room facility, and it is being attached to the descent stage in that facility here at Kennedy Space Center. You see to the right here, the booster is being delivered. It shows up on a cargo plane. These are all quite historical events that we get to see here. I'll try to stop clicking on this. Something that is also interesting, I think, for this flight is that you could send your name to Mars. So there are some 10 million people throughout the world, and their names are etched onto 3 different microchips. And that's a picture of that in the lower left-hand corner. And then here's another picture of the SLC-41 complex, just a different view, but you can see the rocket being transported out to that central location of the launch pad, and then you see the Atlantic Ocean there in the background. Okay, so what's left for INL to do? What have we been doing down here at Kennedy Space Center, and what's left for us to do? So this particular slide is a big check mark. This was our first activity. We completed it in May. We were down here for about 3 weeks to support this particular activity. So we delivered the power system from Idaho to Kennedy Space Center and received it in the RTGF facility. So this is a facility that's only used for this activity. You see that in the center picture here. And to the left, you see a photo on the inside of that facility of the receipt team down here at Kennedy Space Center. And I also recapped the transportation trailer that we use to transport down to Kennedy Space Center and then around the KSC facilities. Now for the hot fit check, it's really another special time for us because it's the first time the nuclear power system will actually power the land rover and its systems. So we literally load the RTG up into the transportation trailer inside a caged assembly. So this is part of a 2,500-pound base that the RTG sits in and that we use to transport it intra-building at Kennedy Space Center or at Idaho for that matter. The picture you see in the middle is actually of the Curiosity rover. It is not the Mars 2020 rover because those pictures haven't been released yet. But this is the INL and Jet Propulsion Laboratory team inserting the RTG into the Land rover. You might ask why it's upside down. This gives us an opportunity to practice one more time, in addition to powering up the rover and its systems in the configuration that it will be during the launch mate. This is in a clean room facility. The clean room facility is the payload hazardous servicing facility, and it's the picture that you see up here at the right. The clean room is the high bay area. The airlock is in front of it, and we roll our trailer up onto the apron, and this is a picture of the trailer for Mars 2020 rolled onto the apron, and we take out the MMRTG that's in the caged assembly. We roll it through this overhead door, and then it's all cleaned again and then inserted in through another overhead door into the high bay area, where another team meets it dressed out in these nice bunny suits and help install it onto the rover. So that's what you're seeing there. It's about a 2 or 3 day activity. In this case, it was done in 2 days. And this gives JPL the opportunity to check out all of their systems on the rover under nuclear power. Okay, what else are we waiting to do? So right now, I'm down here on a 2-week monitoring tour. So we enter RTGF where the MMRTG is stored on a daily basis. It's a nuclear facility. When we take the power system over to PHSF, it too is declared a nuclear facility, so they have to operate, we all have to operate in those nuclear facilities in the same amount of rigor that we would have at INL. We have DSAs that have been implemented. We've gone through readiness reviews to be able to perform the operations in these facilities. So right now we are waiting for the Jet Propulsion Laboratory to take the rover, and you see a picture of the Mars 2020 rover during its system checkout when it first arrived down here back in November. And you see it here. It is upside down in this picture. Let's see, here's the rover over here. It's upside down. The entry, descent, landing hardware is going to be installed on top of it, and then it's going to be encapsulated in this configuration in this picture inside the spacecraft, and the spacecraft is what you see over here. And then it will be encapsulated inside the fairing. And all of this is done right now. It is in the spacecraft and it's waiting to be encapsulated inside the fairing. And we're expecting that it will be transported over to Cape Canaveral Air Force Station within the next couple of weeks. Okay. This next picture is what's left for INL to do. So as I said, we're monitoring it now, the power system now on a daily basis. What's left for us to do? Well, we're going to put it in that caged assembly, put it in our transportation trailer, and we're going to go over to the vertical integration facility. We're going to unload it from our trailer, and you see our trailer here in this picture. Again, this was Curiosity back in 2011, because this has not happened yet here. But we're going to unload it onto this apron, and then we are going to hoist it outside of the facility up to level 7, which is labeled here the MMRTG level. And that level on this side is over here on this mezzanine. We'll land it there. The entire lift has to be done at less than 10-mile-per-hour winds. It's done at the break of dawn. So we roll with our transportation trailer about 2 in the morning. And then we come out here to the vertical integration facility, get it unloaded, put it on the apron, and just wait for daylight. That's when it truly is the least windy here. As you can imagine, we get quite a breeze from the ocean, and we will hoist it up. yes, we can be delayed with weather. You see tag lines right here in the picture. There are 4 300-foot tag lines that are used to hoist this up. Now, all of these components that you see are hoisted up into this facility by this crane. It's a 60-ton crane. And as you might expect, NASA's quite used to hoisting and rigging extremely expensive equipment. So it's kind of interesting. We get some blowback because we like them to practice, and we will go over 2 days in advance of the insertion date to practice with our qualification unit that is unfueled, and we'll go over there to practice that so that they can just kind of get a feel for the light load. It's only 2,500 pounds, and they're always glad at the end of the day that they got the opportunity to do it before they lifted the $74 million fueled unit, of which we only have one, and there are no spares, similar to many spacecraft items, not to mention the Land Rover. So it's important that all of this work be done correctly the first time and without injury to any of the components. And then finally, again, you would see the insertion using this tool of the MMRTG at launch minus 9 days through a 6-foot square fairing door. So in here, you would already find the fairing, and inside of the fairing would be the spacecraft containing the rover. Okay, and then, after that is all we have left is the launch, the cruise, to land it on Mars and start exploring. Here's a map over here. You can easily Google this at KSC launch sites and get many different maps. We are at launch site 41, so that's up here, right, literally on the coast. Here is another picture of the launch. This was, again, Curiosity. Same rocket will be used in Atlas V rocket. It has 1 engine and 5 solid rocket boosters on it. It will take a 7-month voyage to get to Mars this time. You see the cruise stage here. So this is what it will look like as it's cruising to Mars. And then here's an illustration below it of the entry, landing, and descent, the EDL stage, and the rover being lowered with a sky crane down to the Martian surface. If you want to see something exciting, especially from an engineering perspective, it is called, the Jet Propulsion Laboratory calls this descent 7 minutes of terror. And if you go to your browser and search 7 minutes of terror, watch this video. I highly suggest it. And I can't imagine being the engineers that designed it and tested it here on Earth, and the anticipation of waiting all of those months to see if it worked appropriately. So to me, that would be extremely stressful. And then finally down here is a selfie comprised of a collage of many, many pictures stitched together of Mars Land Rover Curiosity that is on Mars roving around now. Okay, so what is the Mars 2020 mission? It, of course, is launching in July of 2020. The launch window is July 20th to August 11th. There has been a 3-day delay from July 17th. So we know now that the earliest day will be July 20th. The launch window starts at 6:30 Eastern time, so pretty early there in Idaho, but I will have a team down here. There will be about 25 of us down here to support the launch activities. We're launching from Cape Canaveral Air Force Station, and then the spacecraft will take its 7-month journey to Mars, landing on February 18th of 21. The landing site is Jezero Crater in Mars. It's kind of exciting. This was a down-selected spot for Curiosity, but they were didn't want to take the risk to land it without being able to see where they were landing. So this particular mission, they have onboard system that they can take photographs as they're coming closer to the Martian surface, and they can better pick what their landing site will be, literally. So they're gonna, they want to land it somewhere that's not pointing and that's going to poke holes in their rover. So they're pretty excited to use this technology for this landing. Another fun fact for this mission will be there is a helicopter on board. It is a technology demonstration. The atmosphere is very thin on Mars. There is a 6-foot wingspan on this helicopter, and I think it rotates at about 3,600 RPMs. They want to just be able to have it hover. That's their whole goal, to see if they can fly anything on Mars. So that's pretty exciting. This is the second of 3 missions. Curiosity was sent to Mars to see if it could find any microbial life, and it did. This mission is returning to Mars, and it will collect soil samples in stainless steel tubes that are located on the undercarriage. So the samples will be tested using the scientific instruments on board and analyzed, and then cached in these stainless steel tubes. And then eventually a sample return mission is in the works, to be planned to bring those soil samples back to Earth. A little bit about some of the other missions and what they're doing now. So New Horizons was our first mission from INL that we supported. It launched January 19th, 2006, took a 9.5-year voyage to Pluto. You see the picture, the first picture that was sent back from Pluto. It continued on to get to its first Kuiper Belt object, the Ultima Thule, on January 1st, New Year's Day 2019. Its mission has just been extended through the end of 2021, and it will continue traveling at about 33,000 miles per hour to investigate other Kuiper Belt objects. Mars Science Laboratory Curiosity, it is still roaming around. You see a picture, which I ended up cutting off inadvertently, but that rover, the picture here that you see is yet another collage of a selfie that it took right before its tallest climb, which I believe it looks like was about 11 feet. So considering the hikes that some of us take in Idaho, 11 feet doesn't seem like a very big elevation, but apparently it is there. So this picture was taken right before it went over that pediment that you see up there on top. So it is still roving around, and we are getting information back from it. What will we be doing in the future? After this launch, we are already starting to get ready for the Dragonfly mission. Eric Clark of my staff will be the project manager for INL, as I'm planning on retiring here in the not too distant future, but he's going to take on the legacy. And this will be an 8-rotor aircraft that will be going to Titan. And it will be launching in 2026, and it will be powered by a finless MMRTG. I had the pleasure of watching Dr. Barnes of U of I give a presentation on this, and he was asked the question about it landing on the Titan surface, and he said that it wasn't going to be as exciting as Curiosity and Mars 2020 land rovers with 7 minutes of terror. He said that an hour and a half of mild concern was how he would portray the landing on Titan versus that of Mars Science Laboratory Curiosity or Mars 2020. So I found that pretty entertaining. Other things that we do, I am a manager in Space Nuclear Power and Isotopes Division. So we have some other activities that we perform for NASA in some more of the work that we do in addition to RTGs and PU-238 production are nuclear power fission systems. So basically is what NASA would like to do is put reactors in space. So you need power to be able to colonize, say, the moon or Mars, which is NASA's ultimate goal, is to put man on Mars. And you also need something that can propel large payloads to that distance, do it quickly. And these are a couple of avenues that NASA has decided to move technology forward with. So we have surface fission power in addition to nuclear thermal propulsion. We have Dr. Doug Burns that works in our division, and he is the program manager for nuclear thermal propulsion, and he is assisted in this area and surface fission power by Andrew Zilmer. He is a recent hire, and he is our new division deputy director. But I just have a couple of slides of information here. We are doing some fuel testing at our treat reactor there at MFC. On that campus, we are testing fuels there. BWXT and Los Alamos National Lab and Oak Ridge National Lab, they're all working in collaboration to make the control systems, the reactor fuel, testing the fuel, and the materials that are needed and designs for these systems. Let's see, what else can I tell you? Oh, here's PU-238. This is just a picture of the BRR cask. We have, I think, 3 of those at INL that are used for shipments. And then you see a neptunium target here that's getting ready to be inserted into ATR. So in June, that would have been when we inserted this very first target. And you certainly can follow us on all of these social media sites. I highly, highly recommend that you take some time to go to some of the NASA sites. Very informative, amazing pictures. You could spend a lifetime just at the NASA websites looking up these missions. I will say that one of my favorite Twitter feeds is the Sarcastic Rover, at Sarcastic Rover. So it turns out they gave Curiosity quite a personality, and I am sure it, as sarcastic as the personality is, that it's definitely a female persona. So that's all I have for you. I wasn't very good about looking at the questions as we went along, but I'm going to focus my attention there. Doing okay on time?
Yep, we've got about 20 minutes, and then on the chat function, people have been submitting questions there.
Okay, and I'm seeing those. I'm sorry, I promised I was going to try to read those at the same time, but I was afraid I wouldn't get through everything. So let me see if I can answer a few of these questions. What's the lifespan of the space batteries? So I will say a couple of things. I know we refer to them as space batteries a lot, but they are generators. They generate power, and not to be confused with the onboard ion lithium battery. So the power system cannot generate power at a rate fast enough to be able to power everything it needs to power directly. So it charges the ion lithium battery that is on board, and then power is drawn from that. They are designed for a 14-year mission life plus 3 years of storage on Earth. So 17 years is what they're designed for. However, they will provide power for decades. So the half-life of the plutonium oxide fuel is 87 years. As long as the system is intact, it will generate electricity. And that is truly evidenced by Voyagers 1 and 2. They have the same technology, although different power system designs, they have the same technology. Each of those spacecraft were launched in 1977. They still generate power and communicate with Earth today. Each of them have 3 150-watt electric power systems on them, so 450 watts of electrical power generated on each of those. Okay, let's see. I think that answered Mr. Wincombe's question. I'm sorry, Tayan. Okay, and then, hi, Catherine. Catherine Riddle asks, are there any plans for future missions to other planets or outside our solar system? So Pluto New Horizons, as I discussed, is outside of our solar system now. It will never be able to catch up with Voyagers 1 and 2, which are already outside of our solar system as well. Let's see, I think that's
If you scroll up on the chat window, there are more.
Okay, scroll up. Gotcha. Let's see. Marty Sadison asks if I can give a sense of the size and dimension of the fuel pellets. Let me go back to a picture of them. I should put something on there that you can see. So here's a fuel pellet right here, the glowing, and it is inside the iridium encapsulated clad here. It is about 2 1/8 inches tall and about the same in diameter. These general purpose heat sources are around 4-inch cubes, and they hold 4 of these fuel clads. And let's see, I think, yeah, so here's a picture of a general purpose heat source. And in this picture, you can see a cylindric cavity. There are 2 of these with openings on opposite sides. So on the opposite side, this one's already been fueled and is inside the general purpose heat source. And then another one has been flipped over, and you see a second general purpose heat source next to it that is awaiting being fueled. The illustration on the left is an illustration of the assembly of it. So you have 2 fuel clads that are inserted inside a graphite impact shell. The graphite impact shell, 2 of them are inserted into one of the general purpose heat source modules. They're called aeroshells. These aeroshells are made out of a material that is called fine weave pierced fabric. It is made by Textron Industries, and we hold the multi-million-dollar subcontract for that material. The material was used by the Department of Defense for missile nose cones. And they continue fabricating it for our use in these general purpose heat sources. Let's see, interesting fun fact about it, it has a negative coefficient of expansion. So the material, as it heats up, it actually shrinks instead of grows. And there's, yes, a story behind how we discovered that. Let's see. Let's see, Marty also asks, when in the assembly process does the unit start generating sufficient heat to require some form of personnel protection from high temperatures? Great question too. So let's see, certainly the general purpose heat sources themselves are thermally hot. So we utilize stainless steel remote handling tools inside the glove boxes. So personnel protection is used throughout the process of unpackaging the fuel clads through assembly of them into the RTG using these remote handling tools. We also use thermal gloves over the glove box gloves inside the module assembly glove box for personnel protection. Certainly we don't want to melt the plastic glove box gloves. So they're used there too. You might find it interesting that the temperature on the outside of the RTG on the cylindrical housing is only about 320 degrees Fahrenheit at the surface here. So when I mentioned that the centerline fuel temperature was 2,700 degrees Fahrenheit, a lot of heat loss after the pellets are placed inside the general purpose heat source. This block, if you were to put an infrared thermometer on it, you would only see about 500 degrees Fahrenheit at the surface of it in an argon atmosphere. And then it is inserted into the central cavity of the power system, which has insulation around it. And the working temperature on the inside of the RTG is about 900 degrees Fahrenheit in this particular system. So if you go back to the Seebeck effect, it's the temperature difference across the thermoelectric semiconductors that generate the heat. So you have that 900 degree Fahrenheit temperature on the inside or on the hot side of the thermoelectrics, and then the coldness of space for the cold side of those thermoelectrics. So quite a temperature difference between the coldness of space and the 900 degrees F that we're seeing there. But again, it's only about 6% efficient. So the residual heat is actually used to heat working fluid in these cooling tubes that you see around it. These cooling tubes are connected to a tube series inside the rover, and that working fluid, which is a type of freon, is that tubing system is routed around the instrumentation on board the rover, and that residual heat keeps the instrumentation warm. Whew, that was a long-winded explanation, wasn't it? Okay. Let's see, in The Martian, the RTG actually figures pretty prominently. This isn't highlighted as much in the movie. Any comments on the importance of RTGs to human missions to Mars? Yeah, I think that you're going to need, it's been identified by many more than me, so not just my opinion. You're going to need different power sources for different systems to be able to colonize Mars. The MMRTG or other RTGs like it are being investigated for powering rovers that would actually be driven by humans to get around the Martian surface to different buildings or different locations where they need to be. So we have done some preliminary studies on what kind of shielding and the design of that shielding that could be utilized between the RTG and the driver of a rover. And, you know, guess what? The rover looks a lot like Curiosity or Perseverance, at least at this point in time. It's what we're using as a model. So I think RTGs will be used in that sense, just not enough wattage to do much good in providing power needs, hence the surface fission power and the nuclear thermal propulsion reactors. Let's see, I think that catches me up with questions. Oh, what cooling capabilities do the transport casks have? Our transportation casks have a glycol cooling, or they have cooling tubes around the outside. And I don't know that this picture is close up enough that you can actually see them, but you can see in this picture, you see some tubing going into the cask. Is what you may not be able to discern is that there are tubes that run on the outside of those casks. And these black tubes are what provide the conduit to get the glycol to those cooling tubes. So inside the transportation trailer, there are several systems that we utilize, one of which is the chiller that runs the glycol through these cooling tubes. So it is always being cooled inside the transportation trailer. We have redundant systems in there. We can haul 2 casks, and each of the casks have separate cooling systems. They can be routed through either system. We also have an electrical umbilical cord and a feed through. So we attach to the electrical output connector of the RTG, and we have data acquisition monitoring equipment inside an instrumentation compartment in here where we monitor the health of the RTG as it's traveling down the road. And then there's a light system on the outside of the RTG, just as you would see on a reefer, that alerts the Office of Secure Transport, who actually pulls our payloads to these remote locations, so that they can see any trouble lights. In addition to that, we send a 6-person team with it to be able to respond to emergent conditions should there be any. So, you know, as you might expect, yes, we have a procedure. If you see a yellow blinking light, it means something. You have a certain amount of time to stop transport and respond to that particular alarm, whatever it might be. This also rolls with 2 diesel generators on it to provide power to the system. There's an automatic transfer switch to get from one generator to the other. There's even a roof hatch in it should something happen that you have to take the cask out of it, and you can't get it out with a forklift through the door. You can lift it through the roof hatch. Let's see. What is the typical heat generation rate for these casks? So these power systems are relatively low heat thermally. So the MMRTGs only they only generate 2,000 watts thermal. The 300 watt class that powers Pluto New Horizons, it was double that, so 4,000 watts thermal. Let's see. Oh, the approval process for nuclear launches. Marty, that is not for the faint of heart. So we have DSAs for the ground buildings. Even at the vertical integration facility, we have ground operations DSA. And then we have what's called an FSAR for the launch itself. So right now, the Department of Energy is going through they're developing a new launch approval process. But all of the federal agencies that are involved or have skin in the game, if you will be involved in this process. So you've probably heard terms like INSRUP, who end up evaluating the analysis that's been done and provides a recommendation to the president on whether or not a nuclear mission should be launched. So that's currently the process. So there's a lot of players, but Tracy Bishop has developed and is working in a working group as we speak to develop the new process that will be more streamlined and look more like a DSA than the launch accident scenarios, which run like 27 different modeling codes for accidents and things like that. So she's trying to get it streamlined so it's not as complex of a modeling exercise as it has currently morphed into. So more to come on that. And we are currently looking forward to having an MMRTG be one of the very first things that will go, or very first nuclear payloads that will be going through that process and it would be to support Dragonfly.
So Kelly, probably time just for one more question. So Kelly's available. She answers her email. I can attest to that, so that we might have to move some of that offline.
Okay.
If you want to pick one, got a couple coming in here in the end.
Okay. Let's see. Is there any paper report in public domain which talks about the cooling of these casks in some detail? Not that I'm aware of. I think we have a system design description that we have for our casks, but as far as I know, there are not any others of this design. I know the BRR cask that is used for transporting neptunium, cobalt, and Pu-238 targets. I don't think they have cooling systems on those, so I'm not aware of any. Oh, you're very welcome, and I hope you guys all enjoyed the information, and I hope you found it informative, and I guess as lively as I can make it without being in person.